Hello, Chemistry 11. Today, what we want to do is just continue on with a little bit of review of what you learned back in Science 10. Now, back in Science 10, remember you had touched upon the Bohr model, and the idea of the Bohr model was that electrons, let's get this out here, circle the nucleus in specific orbits called shells or energy levels. And each energy level could hold a specific number of electrons, and it is the configuration of the outermost electrons that determine the characteristic of each element. Now, you remember back in grade 10, you probably did this. So let's say here was the nucleus. And what you had was you had different shells, and you would have 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and let's say 1 electron in the last one. This last shell, recall from Science 10, this is what we call our valence shell. And the number of electrons, or the electrons in the valence shell, is called our valence electrons. Now, using the Bohrs model, one can explain why different elements give off different light patterns unique from each other. So what do I mean by that? Is I don't know if your teacher showed you this last year, but what you have is if you were to do the spectrum, you notice sodium, hydrogen, calcium, magnesium, neon, they have distinct lines which are unique from each other. So let's say for sodium, you have a lot in the yellow spectrum, but not very much in the red. Compare that to neon. So the question is, why is there distinct lines? And this goes back to the idea of the Bohr model. Because the electrons are in specific shells, what happens is when an atom is excited, or when it is given energy, the electrons gain energy and move to a higher energy level or shell. In order to return to the lower energy levels, the electron must lose the energy that it gained. And this type of light or energy given off depends on how much energy the electron received initially. Now, what do I mean by this? Okay, so if I were to show you right here, so let's say we have an electron, in this case, a hydrogen, and it's circling around a proton. So there are different shells, so different orbits, 1, 2, 3, 4, 5. If we add energy, that electron absorbs that energy and goes to a higher orbit. This is called excited electron. To go back down, notice it lets off a red light. If we add more energy, the electron jumps even more, it gets even more excited, and then it comes back down. Now notice, because it comes back down further than before, it emits a different color of light. So depending on how far it gets excited and how far it comes back down, this is why we get different spectrums of light, because each element has different number of electrons and they each jump to a different orbit. Okay, now because of this phenomenon, the most common use for this type of idea is fireworks. So why do we get different colors in our fireworks? Is that because they're mixed with different chemicals, and because different chemicals have different spectra, what happens is you get different colors when the elements are excited. So if you see a red color the next time you see a fireworks, it's characteristic of strontium. Copper would be a green color. Now, what this has done is led us to a different model of the electron. This is called the wave mechanical model. Now, Today's model of the atom uses the assumption that electrons travel in a wave-like pattern. Now, how did it work? Now, remember I said that light was given off, but light, if you recall back from grade 8, travel like waves and can be bent. Okay? Now, so the idea is, how can an electron that travels in a straight line, how can it give off a wave? Or how can it produce light? How can a straight line object produce a wave-like light? So the idea now is that the electrons right now move in a wave-like motion. And instead of having defined orbits, there is now only a probability of finding an electron in a specific area. Now we use the term orbital. Okay, so what we've done is we're evolving the idea from Dalton, Thomson, Rutherford, Bohr. Now we have the wave mechanical model. So what happens is this: when we use the term orbital, each orbital has a specific shape. Okay, and we designate them with different letters. So the s orbital means that it has a spherical shape. A p orbital is a dumbbell shape. And the dumbbell can exist in 3 different planes: x, y, and z. Now, if you refer to page 291 in your textbook, what you will see is you'll see a diagram similar to what I have here. So we have the s orbital, and then we have the p orbital. Now, notice the p orbital, it can exist as the x, y, and z. It can exist in 3 different planes. Now, there is another one, it's called the d orbital, and the d orbital mathematically looks like this. Now, again, all of these are mathematical probabilities. You don't need to solve them, but all you need to be aware of is the fact that mathematically, the electrons can be found in these specific areas. Okay? Now, each orbital can hold 2 electrons. So the s can hold 2, p can hold 6. Why? Is because you have 3 planes. The x, the y, and the z. And d can hold 10, because if you look at this particular diagram, you have 2 can exist here, another 2 here, another 2 here, another 2 mathematically here, another 2 mathematically here. Okay? Now, so what would the electron configuration look like? So now we would say, if we said something was 2p5, what does the 2 represent? The 2 represents the energy level, or shell. We're still using the Bohr idea of shells, like the first shell, second shell, or first orbit, second orbit. Okay, but now we're saying, okay, what does the P stand for? Is the shape of the probability. And the 5 up here is the number of electrons in that shape. So if I said 2p5, That means in the second energy level or second shell, I have 5 electrons, and the probability of finding those 5 electrons would be in a dumbbell shape around the nucleus. Okay, and that's what the 2p5 means. Now, when determining the electron configurations, or another term for that is orbital diagrams, one needs to follow a couple of rules. One is the off-bow principle. It says completely fill the lowest orbital first before going on to the higher orbital. So what you want to do is, first of all, fill closest to the nucleus. Okay. Hund's rule: if there's more than one orbital at a particular level, one electron goes into each orbital before they double up. And the Pauli exclusion principle says that when an orbital does accommodate 2 electrons, they must have opposite spins. What does that do? Is that it reduces repulsion. Okay, it's like putting the north and the south of a magnet together. It reduces the repulsion. You do not put a north and north together or south and south together. Now, at this point in time, what I would recommend is for you to take a look at this particular page that's been in your handout. So this is what you call an orbital diagram. And so what you have is, in this case, you have, notice, it has, you fill, it gives you sort of a hint on how to fill things up. So let me give you an example here. Okay. So let's say, for example, let's say we have sulfur atom. Okay. Now, the key word is atom. Remember, atom means neutral. So in this particular case, a sulfur atom will have 16 electrons. And that's what we are focused on right now, is just the electrons. So how do I do the electron configuration or the orbital diagram? So remember the 16 electrons. So what we do is we have 16. So we fill from the bottom up. So here it would be closest to the nucleus. Okay. So we fill in the first orbital. Notice there's only one line. So we go 1, 2. The arrows represent electrons, and notice I have one arrow pointing up, the other arrow pointing down. That means it is going in opposite directions. We fill the next one. It's 2s, so 1, 2. So we've drawn 4 so far. Now we keep on moving up. The next one is the p. So what we have is we go 1, 2, 3. The why I spread it out is because since there were 3 there, 3 lines, I spread it out first, and then 1, 2, 3 more. So what I've drawn is I've drawn 2, 4, 6, 8, 10 electrons. We keep on moving up. 10, 11, 12, 13, 14, 15, 16. So how does this look? We have 16 electrons, like what my question was asking for, 16 electrons. We just fill it in. So in this case, for sulfur, I go 1s. I have 2 of them. That's here. Go to my next one. I have 2s, 2. That's right here. My 2p, I have 6. That's right here. And then I have 3s2 right here, and then 3p4. That's the electron configuration. Now, so if I were to do this, I would say that it is 1s2, 2s2, 2p6, 3s2, 3p4. Now, you remember back in the Bohr model, remember you would go, oh, here's sulfur. You would have 2 electrons here, 8 electrons here, 6 electrons here. Notice, how do these match up? I have 2, which is 2. Here, I have 2 plus 6 in the second energy level. That's 8, second shell. And then I have 2 and 4, which is 6 in the third shell or third energy level. This is what you call electron configuration. So we are building upon what the Bohr model's idea was. Now, let me give you one that's a little bit more complex. Let's say if we were to do, oh, I don't know. Let's do chromium. So let's do chromium. Again, we're focused on the atom. Okay, so chromium atom, there is 24 electrons. Okay, so going back to the orbital diagram, okay, I'm just going to erase this so that it makes it a little bit easier, give it a fresh start. So basically, I need to draw 24 lines. So here, I'll use a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, here is where it's different. Notice here, the 4s is a lower energy. Okay, so we fill in the 4s first. That's 18, 19, 20, 21, 22, 23, 24. Why do we fill in the 4s? Because mathematically, it has the lower energy. It might be a higher energy level, but lower energy. So if we were to write it, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So if I were to write this into your notes, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now, in some books, they will write it like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. Notice the difference, okay? Both ways are acceptable, okay? In some books, they write it the first way because they want to acknowledge that the 4s is a lower energy. But in some books, they write it the second way because they want to acknowledge that the third energy level, you want to keep it together. All right, folks, what we'll do is we'll stop it here, and hopefully I will give you come to class, and there will be some homework for you to practice this. All right, folks, thank you very much. Have a good day. Bye-bye.